Hello guys, in this video we are going to talk about linear discriminant analysis. So in the previous video we saw about PCA, that is principal component analysis, and we saw that how can we compress data using PCA. Now from a pattern recognition point of view, just compressing data is not enough. You have classes, so you need something that can separate the classes as well. So say traditionally from PCA point of view, suppose you have two classes. This is my data that I want to classify, and suppose if we apply PCA on this, so what we'll have to do is we'll have to separately apply PCA on this particular class and then separately on this class. So suppose I apply PCA on this, I find its mean, its eigenvectors and so on. So let's say this will be its transformed space. So then what I'll do is I'll project every point over here, and then I will remove E2. That is what we used to do in PCA. Similarly for class 2, this is my class 2 say. So for class 2 also I will have to project it on the transformed space, even E2 space, project the data on some other dimension, the maximum variance direction, and then remove E2. So we'll get something like this when we reconstruct from year to year. Now the question that one can ask is, do we really need to reconstruct? Can we not separate these points itself in the transform plane? So here, because this E1 E2 are different, this is not possible over here. But what if, suppose instead of taking these two classes differently, we combine both of these classes and then take its mean and variance. So what one can do is, instead of taking these separately, suppose that I combine both of these classes and then and then transform. So I'll get a mean, say suppose somewhere over here, and these will be some of my eigenvectors, right? So this is first eigenvector E1, and say this is E2. Okay, so okay, from this diagram I have written this as E1 and this is E2. Okay, so when we do this we can get a space like this. Now you can see, if suppose so you can see that E2 is the direction of relatively lesser variance than E1. E1 has more variance, E2 has less variance. So here you can see there is a problem. If suppose I project all these points on E1, then both these classes will mix up. They will not be linearly separable anymore. Okay, so here there is this problem that if suppose we combine both the classes and then go to the this eigenvector space, then these um, data points get mixed up. That is, they become non-linearly separable, but they were linearly separable in the first case. So what do you mean by linearly separable is I can draw a line which can separate both these clusters. But here, if when I project them on E1 and remove E2, what will happen is both these will become something like this. So there will be an x over here, 0 x 0 x x 0 0 x, something like this will come over here, because both of them are mixing up over here, you can see. So then one may feel this cannot be done. But then if you see, suppose that I, instead of projecting on E1, if I project on E2, if instead of removing E2 I remove E1 and project the data on E2, this axis, then you can see this sort of graph can be acquired. So here I can project every point on this axis, every point on this axis, and you can see now both of these are linearly separable. So this is what LDA is doing. So this is the major difference between LDA and PCA. PCA does not focuses on classes, and if you want to put classes in PCA, you will have to represent every class differently. So you will have to take this class, transform it, then reconstruct it. So these many things you will have to do for PCA. But for LDA, what LDA says is you combine the class and take the mean of the combined class, take its eigenvectors, go into the eigenvector space, and now don't choose the maximum variance axis. Initially PCA used to choose the maximum variance axis. Now don't choose the maximum variance axis, choose that axis which gives you the maximum separability. So here you can see this axis gives you the maximum separability between the two classes. Now for a pattern recognition point of view, from a pattern recognition point of view, it is not necessary to preserve the whole data, because you, after all, what you need to do is you just need to classify. So as long as you are able to classify your data points, it is more than enough. You don't need, so here you can see that the loss will be greater, because if suppose I try to reconstruct this again, so what I'll get is something like this. So I am reconstructing this E2 space again in x1 x2 space. So this is x1, this is x2. Suppose I am reconstructing this again, so this is going to be something like this. So here you can see that this is class 1 data, this is class 2 data. So a lot of data has been lost. You can see this whole portion has gone, this is gone, this is gone, this is gone. But then still they are linearly separable. So a pattern recognition point of view says as long as both of them are linearly separable or they are distinguishable, it is okay. You don't need to save all the data, right? So, and you also don't need to go from here to here. You can separate the data in the transformed space as well. So this is the beauty of LDA. So LDA further minimizes the, what we say, the computation by just discriminating the data in the transformed space. You don't need to go back to the reconstructed space to classify the data. You can classify the data here itself, right? So that computation, which is quite an expensive computation if there are many dimensions. So here you can see the reconstruction equation. The x space will be equal to u, which is a matrix. So here you can see u is a matrix which is having all the eigenvectors. So eigenvector 1 2 3 4, like this. U is a matrix and y is the transformed space. So in order to go from transformed space to the actual space, you have to multiply these two things, and these matrix depend on k and d. What is the dimension of the total matrix, and how much are you basically compressing it, how much dimension reduction you are doing. So this is quite computationally expensive if suppose k is very large, where k is the dimension, right? So so this is what we have got. So it is very important that if we can classify in the transformed space, we can save a lot of computation. So let us see how can we do this. So my objective is to now combine this data and to get a combined transformed space. So this transformed space is for this both of these data simultaneously, and now the objective is to separate the data, to find an axis which can separate the data to its fullest. That is what we want. So that is our objective over here. Find a direction which has maximum separation of classes. Okay, so now let us see some of the notations. So x is my input data. So x is equal to x1 x2, where x1 x2 are the features. Suppose from here I am taking two features, but in general you can have some n number of features, right? So for simplicity I am just taking two features. These are my two features, right? x1 x2, that is the space. wi are the classes, so this can be w1 class 1, this is w2. Y is the projected space. So this space, this E2 space, I am naming this as Y. This is my Y space. Okay. E is the required axis. So now I don't know whether it will be E1 or E2 or any other direction. So I am just naming this required direction as E. So we know that the transformed space will be y is equal to E transpose x. We know this because this is from PCA. So we saw that if we want to transform this from year to year, we need to multiply it with that axis that you want, the dot product, right? So now what do we have? Let us see. So we can get the mean of both the classes. So this will be the mean of this class and this will be the mean of this class, right? So mu I is equal to 1 by n summation of all the x's. So all these summation upon the total number of n over here. So let me make this ni, because so what is ni? Ni is number of samples in omega I. So in omega I, this class, how many samples are there? That is ni. Now mu I tilde, that means the mean in the transformed space. Now because we are going to talk in terms of transformed space only, it is important that we know where is the mean in the transformed space. So that is mu I tilde. So simply that will, because we are in the transformed space, so here there will be y, so it is so mean over here is nothing but addition of all points over here divided by total number of points over here. So the same thing, so here instead of x you are getting E transpose x, because that is y, because this is the transformed space, right? So now this is equal to E transpose by n. So here you can take this out, because that doesn't, this summation only depends on x. So you can take this out and you get this thing. Now you know that this upon this, so basically this full thing can be written as mu I. So you can get mu I tilde, that is the mean in the transformed space, is nothing but you transform the mean. So that is, take this mean and you transform it, that is multiplied with E transpose, and you can get your desired mean. So now there is this first criteria. Also please understand that here I am using only two classes. So we are using LDA for only two classes. We will generalize it for multiple classes in the next video. Okay, so now in PCA what we used to do is we used to only choose the axis that has the maximum variance, but we saw that this will not work in LDA. So here in LDA what we want is we want an axis which is having the maximum separation of both the classes. So by that we can infer that the means of both the classes, say you can see this is mu1 tilde and this particular thing is mu2 tilde. This mean over here is mu1 tilde and this is mu2 tilde. So I can have one criteria that mu1 minus mu2, this particular distance mu1 minus mu2 tilde, should be maximum. So I need an axis such that now I don't require the variance to be maximum. Instead, I require the separation of means to be maximum. So let me take this as a criteria 1. Now, since this is a distance, so I can just take it square also, because this makes things easy. The thing that you are seeing over here is nothing but the norm, the basic norm, the Euclidean distance, what we say. So this is the Euclidean distance between both of these points. So I'm just taking the square because if I don't take it, I'll have to have that root particular thing. So it is very easy to avoid that using the square. And if I want to maximize this, I can also maximize the square and get the same thing. So maximizing this distance or maximizing the square does not make a difference. So now this is mu1 tilde mu2 tilde. So from this particular equation we can see that this equation, that mu1 tilde will be nothing but E transpose mu1 minus mu2 tilde will be E transpose mu2. So what is E? Please remember, E is that required axis where the separations of the means will be maximum. So E is the unknown that we have to find out over here. We have to find out E, which axis gives you the maximum separation. So I have separated these means. So I want a criteria. So this particular thing should be maximum. Similarly, this implies that both of them are equal. So this particular thing should be maximum. So I have mu1 minus mu2 transpose, mu1 minus mu2 the whole square. So I can write this particular thing as this into this transpose. So that is from a simple property, a vector property. So a square, mod of a square is equal to a into a transpose, right? So E transpose mu, so this particular thing we saw that it was E1 E transpose mu1 minus E transpose mu2. So the same thing I have written over here as transpose. Now what I'll do is I'll take this E transpose common, and over here I'm going to apply transpose inside. So we know that when AB the whole transpose, so it becomes equal to B transpose into A transpose, right? So the same thing I've done over here. So this E will come, this E will get multiplied like this. So you'll get mu1 into E transpose, and this will be mu2 into E transpose, and then I can take out this E transpose outside. So also because there is this transpose over here, so both of them will get transpose, and this will go away and this will get a transpose. So this is what I can write. Now I am going to define this particular thing as a term which I am saying as SB, which is scatter between the classes. So this thing over here, this is going to be a matrix. Why? Because this is mu1 minus mu2. So mu1 minus mu2 is nothing but actually this minus this. So remember that there is no tilde over here. So this tilde tells you that we are in the transformed space. But since there is no tilde over here, so we are in the normal space, the x1, x2 feature space, right? So this is going to be, say, some mu1 which will have some value of x1 and some value of x2. So mu1 is going to be a vector of some x1, x2. Similarly, mu2 is going to be a vector of x1, x2. So we can have mu1 minus mu2, which is again a vector which is x1 minus x2, x1, say this, let this be some dash. So x1 dash minus x1 and x2 dash minus x2. So this is what we do as Euclidean space, Euclidean distance. So you can see that this is a vector. When I multiply this with its transpose, so I'll get x1 dash minus x1 comma next element x2 dash minus x2. So this transpose is over here. So this was a column vector, this became a row vector. So now you can see when I multiply this, I will get a matrix, because this is 2 cross 1, this is 1 cross 2. So when I multiply, I will get a matrix of 2 cross 2, right? So over here SB is going to be a matrix, and that I'm going to call it, so there is this name that is given to it, that is scatter between the classes. So this name is just because there is this scatter which is between the classes. So it is between the classes, so between both of these classes how much scatter is there, that is what is given by SB, right? So it is just the Euclidean distance between the two means, that's it, but in a matrix form. So this is what we are getting, right? Now only only separating the means won't work, because see, you can have a case like this. Suppose that I have just took the condition that I am just separating the means and I'm not taking anything else into consideration. So you can see there can be a case like this, where say class 1 data is this is my class 1 data and this is my class 2 data, okay? So here you can see that if suppose we consider a axis like this, so this will get an eigenvector like this in this direction, which is parallel to this, because this is some sort of uncorrelated data, and you will get another like this in this direction, right? So here you can see the distance between these two means is greater in this direction than in this direction. So you can see that the distance between these two means is greater in this direction, but the distance between the two means in this direction is less. But here you can see that there is a overlap. So when I will project all these data in on this axis, here you can see that there will be some overlap, because here you can see that overlap. Both of them will come near to each other. But if suppose I project the space into this axis, here you can see that there is not going to be any overlap. The data will be easily distinguishable, or we can say linearly separable, right? So we just don't need the means to be separated. In addition to that, we also need that the variances should also be taken into account. So here you can see that because this variance is very huge, so we are not able to get a good discrimination on this axis, because there will be a overlap in this region, this particular region. So we want a criteria where the variances are also small. So here you can see on this axis we have small variance but okayish sort of a mean separation. So we need something like this. We need a small variance and an okayish kind of yeah. So by this we get a second criteria. We need to not only separate the means, we need to maximize the means. Basically we need to maximize these. In addition to that, we'll also define a quantity that is scatter. Now we could also use variance, but in some next video I will tell you how does this scatter matter basically. So a scatter is more useful than a variance term over here. We'll see what is a scatter. So define a scatter. So scatter is defined like this. It is summation y belongs to omega I, y minus omega I the whole square. So you can see that in our variance equation, so variance would nothing be but it's a variance of x. So this is x minus x bar the whole square. This is what we write as variance, right? And for matrix it becomes covariance, which is 1 by n summation x minus x bar. So the same thing, because of this particular rule we get x minus x bar transpose, right? Now this same thing is scatter, just that don't divide it by 1 by n. That's it. You don't divide by 1 by n. This much quantity is what we define as scatter. So here you can see that this same quantity is over here, only because I am in my transformed space. So please take care of the notation. Wherever there is a tilde, we are in the transformed space. We are in this space wherever we are in tilde. So because I want to basically minimize the variance in the transformed space, so this will be the variance in the transformed space for this, and this will be the variance. Also, let us use a different word. Let us use scatter over here, because I'm not going to use variance over here. So this will be the scatter. We'll see the difference in some other video. What is the difference between a scatter and a variance, we'll see. So for now, let us go with this. So this is the scatter for this particular class, and this is the scatter for this class. So we see that we need a minimum scatter, because if we maximize the scatter also, what will happen is the classes will overlap on the transformed space. So this axis on which I am projecting the data becomes my transformed space, right? Because here I was projecting on E2, so that was my transformed space. Here I am projecting on this axis, so this becomes my transformed space, or this axis. So now we have a notion of SI tilde square. So now these scatter will be for every classes. There will be this scatter for this class, a scatter for this class. So for two classes there will be two scatters. Also this is scatter between the classes, and this is just scatter. Please don't get confused with the names. So SI tilde square is nothing but this thing which we have defined over here. The same thing we can do from here. This we can break this like this, and take E transpose outside, and we can see that E transpose comes out over here and E comes out over here, because it is independent of the summation. The summation is only depending on X. Now this particular thing, that is X minus mu1 into X minus mu1 transpose, this thing I am denoting as some SWI square. So this is what I say as scatter within the class. So this is a new name that is given to this thing, scatter within the class. I hope you are understanding the terms. This is scatter between the class, which is about the means. So this is telling you how much scatter is there between the two classes, how much the two classes are away. And SWI is saying within the class. Within means inside this class how much scatter is there. So for example like this, inside this class how much is the scatter, inside this class how much is the scatter, that is given by SWI, and we need to minimize this. Why minimize? Because we can see over here, for a minimum scatter we get a better separability, and for a or large scatter we get less separability, we get overlap. So I will stop the video over here. We will continue our discussion in the next video. Thank you so much for watching.